This video is going to cover problems from discussion 7, focusing on stereochemistry. This first one is a little bit review of our reactions we covered in chapter 5. And so what I wanted you to do here was kind of work backwards to get to your starting materials. Remember, for ozonolysis, to start, we want to see the two carbons that are involved in our carbonyls. We want to go ahead and piece those two carbon atoms together. Remember that our hydrogen peroxide and water here, that turned this hydrogen group into the OH group. So it turned our aldehyde into our carboxylic acid. So I know that this carbon is going to have a hydrogen on it, and I'm going to connect this carbon and this carbon together. So it should look something like this. Our next one here, this is our oxymercuration reduction reaction. We know that this follows a Markovnikov addition, and that means that when I make my double bond, this carbon is going to need to be the more substituted carbon. So my options would be making a double bond to the carbon on the left or a double bond to the carbon on the right. If I make the double bond on the left, then that ends up making this carbon involved in my double bond, and that carbon would be more substituted. So I'm going to need to have my double bond here. Now I can see this carbon is going to be the more substituted carbon compared to this one, so my OH will end up on the right position. For the last one here, this is our hydroboration oxidation reaction. We know this follows our anti-Markovnikov addition. So I want to have this OH being the less substituted carbon in my alkene. So my options here would be making a double bond to this position or this position. And if I end up making the double bond here, it's very clear that I have a more substituted carbon and a less substituted carbon. So the OH would end up on this position. If the double bond was moved over here, we would end up with equally substituted carbons and therefore a mixture of products. This next one is looking at assigning R and S for every asymmetric carbon. And so now let's go ahead and assign priorities and rank them. For my first one here, I'm comparing a fluorine to 3 carbon atoms, then a carbon that's connected to oxygen versus a carbon that's connected to carbons, versus a carbon that's only connected to hydrogens. So for ranking here, I'm going to have 1, 2, and 3, and 4. Notice 4 is coming towards us, so whatever letter I see, I'm going to need to flip it to the opposite letter. So 1 to 2 to 3 would be R, 4 is going towards us, so what this really needs to be assigned as is S. You could also redraw this one if you wanted to, right? Essentially take it over and flip it like a pancake. You would end up having something like this, and now your fourth priority is going away from you, and it's now maybe a little bit easier to see that this is S. For our next one over here, let's go ahead. I'm going to draw in my implied H. Since it's the bond that's missing, I know that the hydrogen has to be going away from me. Now let's assign my priorities. So chlorine beats carbon. This carbon has hydrogens. This carbon has a chlorine. Lowest priority is going away, so that makes this one R. For my next one, let's draw in our H. My H is coming towards me. So that means my fourth priority is coming towards me. Whatever letter I see here, I'm going to need to flip. So this looks like it would be R. That means it needs to be S. For our bottom one, again, let's draw in our hydrogen, assign our priorities. My fourth is going away from me. Perfect. I can see that then this would be going in the correct direction, so R. Now for this one, if I assign my priorities, bromine beats oxygen. I have a carbon with 2 hydrogens versus a carbon with only 1 hydrogen. So I know that this is going to be 3 and this is going to be 4. So now I'm going to have to redraw this in some way. You can go ahead and use the method in lecture that we switch 2 groups. I'm going to go ahead and hold my third group's bond in the plane, and I'm going to rotate until I can get my fourth group to be going away from me. So all I did was imagine holding that bond with 3 and then twisting these 3 groups. So that means that my ethyl group here is going to be going away from me, my OH is coming towards me, and then my bromine is going to be in the plane of the board. Now I can see that my fourth priority is going away from me. In order to get from 1 to 2 to 3, that means we can assign this as R. So in this case, since I rotated, I didn't switch any groups. As long as I have my fourth group going away, I can go ahead and assign my priorities, and that's going to match my original asymmetric center. For my next one here, let's go ahead and rank. Now for this one, remember this is a carbon connected to an iodine and 2 hydrogens. That's going to beat a carbon connected to 3 bromines. And then that is going to beat a carbon that has a hydrogen on it. So in this case, my fourth group is coming towards me. So whatever letter I'm going to see, I'm going to need to flip it. So this looks like R. That means it's going to end up being S. Last one, this is another example where my fourth group is going to end up being in the plane. So I can already tell my hydrogen here. So I redrew this. So this time I rotated my hydrogen to this group. My ethyl group's going to be coming towards me, and my methyl group's going to be in the plane of the board. Now, when I assign, I have 1, 2, 3. That's going to end up being S. This next question, I made small changes to our reaction conditions from Chapter 5, and I want you to be able to predict products based on these small changes. For this first one, I see that I have a halide and I have an oxygen-based nucleophile. So what I wanted you to compare this to was our Br2 and water reaction. So I know that we're going to end up having my oxygen-based nucleophile attack the more substituted position, and the bromine's going to end up on the less substituted position. In order to get to my final product, I need to remove one of these H's. And so in this example, an iodine is going to end up going to my less substituted position, and the OCH3 group, because we want to remove the hydrogen, is going to be on my more substituted position. For the bottom one, here is our oxymercuration reduction reactions. Normally this is done with water as a nucleophile. In this case, we're going to end up using our methanol, and so this is the group that's going to end up being added to the more substituted position. So I wanted you to compare it to our normal conditions with water. This is going to end up adding the OCH3 group to the more substituted position. These two functional groups here with the oxygen, these are known as ethers. For this next one, we're looking to identify any sp3 carbons that are connected to 4 different groups. So anytime I see a carbon that has 2 hydrogens on it, I know that I can eliminate that. 3 hydrogens, 2 hydrogens, 2 hydrogens, 3, 2, and 3. This is the only position with 1 H. Now I need to make sure the rest of the groups are different. I have a methyl group versus an ethyl group versus a propyl group. So this is indeed an asymmetric carbon. Since it only has 1 asymmetric carbon, I can recognize this as being either R or S, and so this is going to be chiral. Pretty much the same idea with this next one. So I have carbons with multiple H's here. This is the only carbon that has a single H. So its 4 groups are a hydrogen, a bromine, this propyl, and a methyl. So here is my 1 asymmetric carbon. This again can be R and S, so that means it is chiral. For this one, I do have 2 asymmetric carbons, and so you might need to draw in your H's going away from us to see that, but this pathway, these 2 carbons look the same, but then these 2 carbons look different, versus if I'm comparing this pathway, these 2 carbons look the same, but then these 2 carbons are different. So these are both asymmetric carbons because they're connected to 4 different groups. However, this molecule has a plane of symmetry. I can fold it in half and get identical sides. That means its mirror image is going to be identical to this structure, and so that makes this molecule achiral. For this one, again, if we're identifying the asymmetric carbons, we're going to want to start with carbons that only have 1 hydrogen, and so we're going to have 1 hydrogen at this position, and this position. So those are our 3. I think it's probably straightforward to see this carbon has 2 H's, 2 H's, and 2 H's. Now this position does have 1 H, but it ends up having 2 methyl groups connected to it, and so this would not be an asymmetric center. Now that I know that I have 3 asymmetric centers, I can use my formula, 2 to the 3rd power. That means I have a total of up to 8 stereoisomers here. For my next one, notice all of these carbons in my 6-membered ring here. These are going to be sp2 carbons. And so I'm going to ignore these carbons as potential asymmetric centers. I have a carbon with 3 hydrogens. This is the only carbon here that has an H on it, 4 different groups. And so here's my one asymmetric carbon. This molecule could be R or S. So 2 to the first power, we have 2 possible stereoisomers. This next one is getting some practice using the antiomeric excess formula. This first one's kind of a trick. Remember that if we have exactly 50% of our minus enantiomer and 50% of our plus, these are going to rotate one direction, these are going to rotate in the opposite direction, so we'll end up seeing is 0. This is a racemic mixture. For the bottom one, I'd see that I have an excess of the plus enantiomer. I'd want to go ahead and subtract this difference, so I'd see that I have an enantiomeric excess of 50. I can go ahead and then now plug that number in, subtracting these two. I know that my pure enantiomer would end up having a positive 158. That means here I'm going to go ahead and look for my mixture. When I solve this, it's going to be half of this number, so we should see plus 79 as the specific rotation. This next one was more practice with RNFs, so I'll quickly assign here. So I know my hydrogen's going away from us. That means that I'm going to end up seeing this one as S. My hydrogen, again, is going away if I rank my priorities. This one then is going to be R. Now for the bottom part, what I'm asking here, draw a stereoisomer that has the same melting and boiling point. What you needed to know here was that enantiomers have the same melting and boiling point, same physical properties. So what I'd want to see here is the mirror image of this structure, which you can easily draw by switching the hydrogen and the bromine here, and the hydrogen and the chlorine here. So we can put both of those on a dash. Now that would make this one R where the bromine is, and this one where the chlorine is S. So if this box was for the enantiomer, here we're looking for stereoisomers that have different melting and boiling points. So this is where you would draw your diastereomers. And you have 2 different possibilities here. We can switch the carbon with the bromine, or we can switch the carbon with the chlorine on it. And so in this case, I switch the bromine one. This would be a diastereomer. I could also keep the stereochemistry at the bromine the same and change the position at the carbon where the chlorine is. And so these are, either of these possible answers would be correct. This last one is more practice with curved arrows. I know that I'm going to end up using one of my alkenes here in order to get this reaction started. And so what I need to do here is make sure I'm looking at, I have this alkene as a possibility or this alkene. And it should be a little bit easier to see that if I'm trying to figure out which alkene's left in my product, it's going to have to be this alkene. Right here is the 1, 2, 3 carbons, 1, 2, 3 carbons. So you could tell by looking at this, but the other thing we'd want to do is we actually do want to start this by making the most stable carbocation. If I add the hydrogen to this double bond, I'm going to end up making a tertiary. If I add the hydrogen to this double bond, I'm going to end up making a secondary. So a couple different ways you could tell that we're going to actually start by using these pi electrons to go ahead and get protonated. We're going to add that hydrogen to the less substituted position. That's going to end up making a carbocation here. Now, if I wanted to look to see how I can piece this together, these alcohols are actually identical, right? They both are bonded to the same carbon. They both have a CH2 and then an OH on them. I'm going to go ahead and track my specific carbons in my ring here. And the other thing I'd like to notice here is notice carbon 1 here, that has 2 methyl groups on it. The only carbon that is connected to 2 methyl groups here is going to be this one, and that's going to be the carbocation that we've made from the addition of that alkene. Now I can see I can use either one of these OHs. Let's go ahead and count our atoms here. So now I can see I have an oxygen that's bonded to carbon 4 and carbon 1. So I'm going to go ahead and use these lone pairs to make a new bond to carbon 1. Now I end up having one more step in order to get to my final product. I can go ahead and use the water, the conjugate base of my original acid, take that hydrogen, push electrons onto that oxygen to get my final product.